In the previous lecture, we saw a proof of Poincare duality for manifolds with finite good cover. So let us recall the theorem. Let M be an orientable manifold of dimension n then the pairing HIM given by omega comma eta is mapped to integral over m omega batch eta. This is a compactly supported form, and so we can integrate it. Top form is non-degenerate. So let S contained in M be let M be as above. So let M be an orientable manifold of dimension n with a finite good cover. Let S contained in M be a compact orientable submanifold let K be the codimension of S, that is dimension of M minus dimension of S. So then we can use S to define a map H n minus K M to R. So how do we define this map? So let omega be a class in Hn minus Km. Then omega restricted to S is n minus K form, which is a top form on S. And since S is compact, we can integrate this. On S. So thus the map is given by omega is sent to integral over S, omega restricted to S. This gives an element in H n minus K M dual and since M is assumed to be a finite type, The cohomologies and compactly supported cohomologies are finite dimensional, as we saw before. And Poincare duality says that there's an isomorphism h n minus k m to h k compactly supported m dual. So taking dual of this, we get hk compactly supported m to hn minus k. So there's an isomorphism. Thus, the above map defines a class in hk compactly supported M. So we denote this class by eta sub s. It has a defining property that for all omega in hn minus km, we have integral over s, omega restricted to s, is equal to integral over m eta s wedge omega. So let us see two examples. So let us compute the cohomology class of a point P. This is a submanifold of codimension n, and so thus its cohomology class eta p will be in Hn compactly supported M and has the defining property that for all omega in H naught M, we have integral over P, omega restricted to P, is equal to integral over M eta P wedge omega. Since omega is in H naught M, it is represented by a constant function. So thus, if we take eta p to be a bump n form which integrates to 1 on M, then it satisfies the above property. Thus we can so we may take eta p to be any such. So next, let's compute the cohomology class of M. So assume that M is compact, and let us compute the cohomology class of the submanifold M, which is a submanifold of codimension 0. Thus, in this case, the cohomology class M is going to be an element of H0 compactly supported M and has the defining property integral over M omega is equal to integral over M eta M wedge omega for all omega in H and M. So clearly, we can take eta M to be the class of the constant function 1. Okay, so we will come back to these cohomology classes later. These cohomology classes have some nice properties with respect to transverse intersection, and we will see those later. So for now, next we shall use the same idea that we used to prove Poincare duality to show that Kunneth formula holds. So let X and Y be smooth manifolds. And let P1 and P2 denote the projections. These gives maps P1 upper star from H star X to H star X cross Y, and P2 upper star from H star Y to H star X cross Y. Thus, we get a map H star X tensor H star Y to H star X cross Y given by alpha I tensor beta I summation over I maps to summation over I P1 upper star alpha I wedge P2 upper star beta I. So the theorem, which is known as Kunneth formula, The above map is an isomorphism. So proof. So we will prove the theorem. In the case when X has a finite good cover. The proof is by induction on the cardinality of the finite good cover if the cardinality is 1, then X is the Fermat vector Rn, and in this case the theorem is equivalent to saying that pi upper star from H star X to H star X cross Rn. Okay, I should write, yeah. Oops. So we have Rn cross Y. Let's call this map pi. Is an isomorphism. So here so we know that pi upper star from Hi Y to Hi Rn cross Y is an isomorphism. This is something which we had seen earlier, and Hi, so this pi upper star we can write it as, this statement can be rephrased as saying that is an isomorphism. But this is same as saying that direct sum, let's say alpha plus A plus B. Is an isomorphism. So thus this Askunth formula is true when x equal to Rn. So let us assume that it is true when x has a finite good cover of size less than equal to p. Now assume that x equal to I equal to 1 to p plus 1 ui is a finite good cover of size p plus 1. We let u equal to I equal to 1 to p ui and v equal to up plus 1. So the result is true for u, v and u intersection v. So by this we mean that direct sum q plus r equal to n hq u tensor h r y to h n. U cross y is an isomorphism. Similarly for v and u intersection v. And we want to show that this is true for x. So we have a long exact sequence the Mayweather sequence H HQ U directs M HQV HQU intersection V HQ plus 1 X HQ plus 1 U directs M HQ plus 1 V and so on. So tensoring this with H R Y we get a long exact sequence. HQ U directs M HQV tensor HR Y HQ U intersection V tensor H R Y HQ plus 1 X tensor H R Y HQ plus 1 U directs M HQ plus 1 V tensor H R Y and so on. So let us denote this long exact sequence by L Q comma R. For an open set U contained in X, or let's say W contained in X, denote by w tilde the set w cross y. Then we have the long exact sequence. H q plus r u tilde direct sum h q plus r v tilde h q plus r u intersection v tilde h q plus r plus 1 x tilde h q plus r plus 1 u tilde h q plus r plus 1 v tilde, and so on. So let's call this sequence M. Then we have a map LQR to M. Using the maps HQ U tensor HQ HR Y to HQ plus R U cross Y, given by alpha tensor beta goes to P1 upper star alpha, which P2 upper star beta. So let us check that. Let us check that this map gives a commutative diagram or this map gives a, let us check that this is a map of two long exact sequence. That is, we need to check that certain diagrams commute. So we need to check that the following three squares commute. So the first one is HQ U direct sum HQ V tensor HRY to HQ U intersection V tensor HRY HQ U tilde direct sum HQ V tilde to this Q plus R HQ plus R U intersection V tilde. The second square is HQ U intersection V tensor HRY HQ plus 1 X tensor HRY HQ plus R U intersection V tilde to HQ plus R plus 1 X tilde. And the third square is HQ plus 1 X tensor HRY to HQ plus 1 U direct sum HQ plus 1 V tensor HRY, and this maps to H Q plus 1 plus R U tilde direct sum H Q plus 1 plus R V tilde, and this maps to H Q plus R plus 1 X tilde. So it is clear that squares 1 and 3 commute. So the only check required is for square 2. So let us check that square 2 commutes. So let's give these maps some names. A, B, C, D. And recall, so consider an element of the type alpha tensor beta in HQ U intersection V tensor HRY. So then alpha is represented by a form and beta by another form. Let rho U and rho V be partitions of unity, be a partition of unity. Subordinate to the cover U comma V, then the image of alpha in H Q plus 1 X is an element alpha prime such that alpha prime restricted to U is equal to D of rho V. Okay, so maybe we should call this map E. Alpha and alpha prime restricted to V is equal to minus D of rho U alpha. So then we have beta compose A of alpha tensor beta is equal to P of alpha prime tensor beta. This is equal to P1 upper star alpha prime wedge P2 upper star beta. But now let us check that. Let's see what is P1 upper star alpha prime wedge P2 upper star beta restricted to U tilde. This is equal to P1 upper star alpha prime restricted to U tilde wedge P2 upper star beta, which is equal to P1 upper star of alpha prime restricted to U wedge P2 upper star beta, P alpha prime restricted to u we know is this equal to p1 upper star of t rho v of alpha which p2 upper star beta, and since d of beta is 0, therefore t of p2 upper star beta is 0, so this we can write as t of p1 upper star of rho v alpha wedge p2 upper star beta. And finally we can write this as t of rho v tilde of p1 upper star alpha wedge p2 upper star beta, where rho v tilde is equal to rho v compose p1. Similarly, we can check that p1 upper star alpha prime wedge p2 upper star beta restricted to v tilde is equal to minus d of rho u tilde p1 upper star alpha wedge p2 upper star beta. Since rho v tilde equal to rho v compose p1 and rho u tilde equal to rho u compose p1 are partitions of unity, subordinate to u tilde comma v tilde, it follows that the square 2 commutes, because recall that E is the connecting homomorphism. So that's exactly the definition of E. E is the connecting homomorphism, and E of an element gamma is the unique element such that E gamma restricted to u tilde is equal to T of rho v tilde of gamma, and E gamma restricted to v tilde is equal to minus T of rho u tilde gamma. So thus there is a commutative diagram of long exact sequences L, Q, R to M, and now we just take direct sum over Q and R, so this implies L, Q, comma R to M, and by induction on the cardinality of the good cover, we conclude that Coulomb formula holds. So this completes the proof of Coulomb formula, and we will end here.